molecular forces. A, for molecules with the same molar mass, and I would say plus or minus 5%, so similar, if not the same. The order of IMFs is LDF, dipole-dipole, hydrogen bonding, and then ion-ion forces. And so a typical question you might get on the homework or on an exam is about rank the following from lowest to highest boiling point, TB. So lowest to highest boiling point is lowest to highest total intermolecular forces. And to help you do the total IMF, it's always important to remember which one is the dominant or largest intermolecular force. So when solving problems, if LDF is the largest one, then it will be less than something that also has dipole-dipole, then hydrogen bonding, then ion-ion forces. It gets a little trickier than that, remember, because if there are two things that have LDF, then you have to look at molar mass, because two things with LDF, one can have a higher boiling point than the other. Dipole-dipole, if you're looking at dipole-dipole and you have two things that you think are both dipole-dipole, which almost never happens, by the way, but if it did, the way to tell them apart is, so delta electronegativity, the larger difference in electronegativity leads to a larger IMF and a higher boiling point. Hydrogen bonding, so again, almost never run into cases where you have two things that are hydrogen bonding, but if you did, you would look to the total number of hydrogen bonds per molecule. So if one has one hydrogen bond and the other molecule can form two hydrogen bonds with other molecules, then the one with two hydrogen bonds possible per molecule would be larger. And ion-ion forces trends is something we're about to talk about. But a typical problem, rank the following from lowest to highest boiling points. So our analysis goes something like this. So non-polar, for anything that contains just carbons and hydrogens. So only LDF, and LDF as its dominant or largest IMF. Here we have CH3CHO. We're not sure what that looks like, or maybe we are, but if you're not sure, always draw the Lewis structure. Lewis structure for this. And the pencil didn't really leave myself enough space. So this one has C double bond O. It does not have oxygen bonded to and covalently bonded to a hydrogen. It cannot have hydrogen bonding. This is dipole-dipole forces. Here we have an OH on the end, that's an alcohol. And you're going to have Lewis structures drawn for you on the homeworks and definitely the exams. There may be some homework problems where I give you names and you have to Google them or look them up or use what you've been taught in the class to figure out what the Lewis structure is. All right. We have an O with a pair of electrons. We have an H covalently bonded to an O. This can hydrogen bond with other molecules of itself. Well, the dominant one is up top for some of them. And I don't know what this is, or maybe you're wondering what this is, but the thing to key in on, it has a lithium, it has a metal, it has a lithium ion. This, I don't care what it is, if it's got a metal ion in it, if it's got a metal in it, it's going to be an ionic compound and have ion-ion forces. So when it says rank the following from lowest to highest boiling point, so let's call 4 has the highest boiling point. That's ion-ion. 3 is going to be hydrogen bonding. 2 is going to be dipole-dipole forces. And 1, nonpolar LDF. Okay. And so that's the kind of analysis we're going to ask you to do on the exams. So you're going to have to be able to look, draw Lewis structures, interpret polar versus nonpolar. That's where we're going. So that's the first thing, is just the types of questions we're going to ask. And on exams, what I've found is the best way to do this is just to ask you 2 at a time. So you won't be ranking 4, except on the homework to get an idea of how to work them. Next detail about intermolecular forces. For large molecules, nonpolar forces, those are LDF, can be large enough to cause a substance to be a solid. So my example is C20H42. If we were to draw something with 20 carbons here, and I'll save us the time of doing that, we would be extremely long. Let's see. So it'd be like a long squiggly molecule like that with hydrogens off to the side. If you think about another one of those next to it, there are lots of opportunities, lots of surface area of interaction. For LDF, which leads to lots of LDF, and therefore this is a solid at room temperature. On a per instance basis, LDF is the weakest, but just like we saw with DNA and hydrogen bonds, get enough of them together and you can turn nonpolar substances solid or have them be solid. See, ionic forces are always the largest, so hands down, they have the biggest charges. Remember, hydrogen bonding is just a large version of dipole-dipole. These have partial charges. Permanence, that's less than full permanent charges. And then nonpolar has random fluctuations leading to instantaneous dipoles. Those are the weakest. Now, okay, so that's the main 4, and those are always the answers for boiling point questions for all those properties we started out in lecture outline 11 video 1 talking about. And then I sort of separated solubility, and I'm going to come back to this picture that we've seen before of the hydration shell of solvent water molecules around an ion and talk a little bit about how this affects solubility. And first off, again, when you're talking of ion dipole forces, the only question you can ever answer, and I hardly ever ask it, but if I do, is about solubility. And for what's going to happen is that the ion dipole force is going to be important in allowing ionic compounds to dissolve in water. Okay. And as noted down here, +1, -1 ionic compounds, there's enough of these partial negatives and partial positives that when you form a hydration shell, ion dipole forces can generally overcome the ion-ion forces and cause +1, -1 compounds to dissolve. And that's like a quick and dirty summary of your solubility rules, by the way. It's not 100% accurate, because there are some +1, -1s that are insoluble. There are also some other compounds with other charges that are soluble as well. But what this is going to say is +1, -1 tends to be soluble, +2, -2, +3, -3. So we said +2, -2 have 4 times the ion-ion forces. That's going to be too much for these partial water hydration shells to rip apart or overcome the charges. So tend to be insoluble. Now, more about solubility. Non-polar compounds are what are called hydrophobic. Hydro means water, phobic means fearing. They are not generally soluble in water, and hydrophobic compounds are almost always nonpolar. Okay. Polar compounds, which have dipole-dipole forces, are hydrophilic, water-loving. And they are generally soluble in water. And so the end result that I like to remember for solubility is like dissolves like. And that means that nonpolar compounds tend to dissolve in each other. This is very good. Gasoline that goes in automobiles tends to be a mixture of nonpolar compounds, all of which dissolve in each other. We'd hate for one of them to become insoluble and then clog up our gas tank, gas lines, etc. Nonpolar compounds tend to dissolve in each other. Polar and +1, -1 ionic compounds tend to dissolve in each other too. And if you've ever heard of water as the universal solvent, it is not universal, but it refers to the fact that a great many things dissolve in water. Nonpolar things do not, and +2, -2, +3, -3 ionic compounds do not. But most often, those are not the things we're interested in.